Hello, I'm Kukuruza. Today, I would like to talk about a sort of universal trig substitution that will be your lifeline in case all else fails. This substitution will let you convert a rational trigonometric expression into a rational expression of a single variable, which will involve no trig, and the antiderivative of which can be found in most cases with a simple algorithm. The trig in question is the Weierstrass substitution. I will begin with a bit of a prelude. A student once came to me asking for help on a particular antiderivative problem. It was finding the indefinite integral of the secant of x. So we put our heads together for a bit, and we were unable to find the antiderivative. We tried using trig identities, different common substitutions, and an array of other logical integration techniques that felt natural. The integral did not yield to our solve, however. This is when we either ran out of patience or time and looked up the solution online. The solution involved making the following substitution, which fit like a glove and meant the antiderivative problem trivial, but this substitution did not sit right with me. It felt like cheating. It felt almost like a show that teaches you what to do when you're lost in the wilderness, telling you to find a rock that has the perfect map of the area just sketched on the back. A trick that might work in that particular case, but doesn't have any skill and logic behind it, and cannot be recreated again for similar problems. So this is when I found the Weierstrass substitution. The theory behind it is that there are these tangent half-angle formulas that everybody who has taken a pre-calculus course has seen before. These two can be rearranged so that you get cosine and sine expressed as a function of the half-angle tangent. Now this is exciting because now if you make the substitution of t is equal to tangent of x over 2, you can represent sine and cosine as rational expressions involving t. This trig gets even better, since differentiating the substitution we get that dt is equal to 1 over 2 times secant squared of x over 2 dx, from which we can express dx as an expression of tangent of x over 2, and therefore an expression of t. Now, any rational expression of sine and cosine can be expressed as a rational expression of t. Now that we have this under our belt, let's take a look at an example. So we have integral of secant of x dx. Then we would like to express it as a rational expression of sine of x or cosine of x. In this case, it's just going to be cosine of x. So it's going to be dx over the cosine of x. Then we learned that if we do the substitution as t is equal to tangent of x over 2, then we can say that the cosine of x can be expressed via that t, and it will be equal to 1 minus t squared over 1 plus t squared. And dx, we can either remember or derive it. This is not very difficult. We know that it's equal to 2 dt over 1 plus t squared. So that means that over here, I can write the integral of, I'm going to deal with the cosine first. So I'm just going to take this expression and I'm going to put in 1 plus t squared over 1 minus t squared, right? Because I have 1 over cosine. So this expression is just going to be flipped, times dx. I know what dx is. 2 dt over 1 plus t squared. So then 1 plus t squared cancels out. So then we have 2 times the integral of dt over 1 minus t squared. Right? And this is very kind of a lucky example because we got a nice cancellation here, and now it's just a matter of decomposing this fraction into partial fractions. As a matter of fact, I will move this 2 back into the fraction because that's going to make the partial fraction decomposition slightly cleaner. So you have 2 over 1 minus t squared, and we would like to express this as a over 1 minus t plus some constant b over 1 plus t. And we can do this, of course, because this is a difference of 2 squares. So then we can say that right here you would need to multiply the top and the bottom by 1 plus t, and here you'd need to multiply the top and the bottom by 1 minus t. Which means that you have 2 over 1 minus t squared is equal to a times 1 plus t plus b times 1 minus t. This whole thing is over, oops, sorry, that's a bit ugly. This whole thing is over 1 minus t times 1 plus t, which is 1 minus t squared. The denominators are the same here, so we're just going to say that the numerators are equal. So I'm going to say 2 is equal to a plus at, and I'm just distributing here, plus b minus bt, which suggests that 2 is equal to a plus b plus a minus b times t. Now, here we understand that the 2 must be the same as a plus b, because that's just a constant, and then the coefficient of t must be 0, because there's no t on this side, on the left side. So we have a plus b is equal to 2, but a minus b is equal to 0. From this, we get that a plus b is equal to 2. This we're not going to change, but a is equal to b. Therefore, a plus a is equal to 2. And a is equal to b. And therefore, a is equal to 1, excuse me, and b is equal to 1. So there you go. Now that means that from all the way up here, we go all the way down here, and we get that we get the integral of, so a over 1 minus t, a is 1, so 1 over 1 minus t, plus 1 over 1 plus t, right, so b over 1 plus t, and dt, which then this turns into the first fraction turns into minus the natural logarithm of the absolute value of 1 minus t, and the second fraction turns into plus the natural logarithm of the absolute value of 1 plus t. We don't forget our favorite plus c, of course, which then this turns into, using properties of logs, or as a matter of fact, let's insert one more step. Let's write this c as the natural logarithm of some c. So over here we get minus natural logarithm of 1 minus t. Plus the natural logarithm of the absolute value of 1 plus t plus the natural logarithm of c, which then we get, according to the properties of logs, right? This is a minus log, so it'll go to the denominator. This is plus log, so it'll go to the numerator. And once again, plus log, so it'll go to the numerator or just, next to it. So then we get the natural logarithm of c times the absolute value of 1 plus t over 1 minus t. Or the natural logarithm of c times, right, what was t? T was tangent of x over 2, so 1 plus tangent of x over 2 divided by 1 minus tangent of x over 2. The solution that I mentioned before produces the following expression. And this is what we got. These expressions do not look the same, but yield the exact same values for all values of x. Here are some plots that are produced. So in closing, the Weierstrass substitution is very useful when you need to find the antiderivative of a function that consists of a rational expression containing sines and cosines, and you have not found a better solution. The solutions that you'll get from using the Weierstrass substitution, they will always work, but sometimes they'll get extremely messy. Thanks for watching.